section 1.4, the matrix equation AX equals B. The matrix equation AX equals B. Linear combinations are one way of viewing matrix vector multiplication. In other words, when we want to multiply a matrix times a vector, we can do it by just doing the appropriate types of linear combinations. And so here's specifically how we're going to do that. If A is an m by n matrix with columns a sub 1, a sub 2, all the way through a sub n. Okay, so those a's represent columns. Keep that in mind now. And if x is a vector in the n-dimensional vector space of real numbers, then the product of matrix A and vector x, denoted by AX, is the linear combination of the columns of A using the corresponding entries in x as weights. So we'll have x1 times A1, then we'll have x2 times A2, and so on all the way through an times x sub n. Okay, so here's an example where we see this matrix times vector multiplication. Suppose we have the matrix 1, negative 4, 3, 2, 0, 5 times the vector 7, negative 6. Now what we're supposed to do here is we're supposed to take the columns of that matrix and do appropriate linear combinations using the entries in the corresponding way of the vector. So take them in order. You're going to take the columns from left to right, and then in the vector you're going to take the entries from top to bottom. So our first linear combination is going to be 7 times the vector 1, 3, 0, and then to finish it'll be negative 6 times the vector negative 4, 2, 5. Now, since we're dealing with just constants here and we don't have any variables, we can actually go ahead and actually perform this numeric multiplication here. So let's multiply that out. The first linear combination is going to give us 7, 21, 0, and then the next scalar multiplication is going to give us 24, negative 12, and negative 30, and now we just add the corresponding entries, giving us 31, 9, and negative 30. Here's another example. Write down the system of equations corresponding to the augmented matrix that you see below, and then express that linear system of equations in vector form, and then finally write it in matrix form. So we've got these 4 different equivalent ways of writing a linear system. You can write it using an augmented matrix, you could write it using a system of equations, you can write it using a set of vector equations, and you can write it as the matrix equation, matrix A times vector x equals B, where B is a 3 by 1 vector in this particular case. So let's look at a way of converting this augmented matrix into those other 3 forms. For starters, let's come up with a system of equations. You can see here that what we're doing is we're taking the numbers in that augmented matrix and using them as coefficients for a system of equations where we just take the variables in order, x sub 1, x sub 2, x sub 3, with the appropriate signs. And then for the final part here, you have a 9 and a negative 2 in the augmented matrix, and the 9 and 2 in the augmented matrix become the 9 and negative 2 that are on the right-hand side of our system of equations to the right of the equal sign. Okay, so that's the system of equations. It ends up being 2x sub 1 plus 3x sub 2 plus 4x sub 3 equals 9, and then negative 3x sub 1 plus x sub 2 equals negative 2. Now for the vector equation, what we're doing here is you're taking that augmented matrix and you're taking it in columns. Break it up into 4 columns. The first 3 columns become a linear combination of x sub 1, x sub 2, and x sub 3 variables. And then you have your equal sign. And then on the right-hand side, you take that final column of the augmented matrix and make it the constant vector that goes on the right-hand side. We've run out of room here, so to get the final equivalent form here, which will be the matrix equation, matrix A times vector x equals vector B, we're going to go on to the next slide. Here's a quick look at the matrix equation that is equivalent to the augmented matrix you see above. What you do here is you take the portion of the augmented matrix that corresponds to the coefficient matrix, that is everything except for the 9 and the negative 2 on the right-hand side. Take that regular part of the augmented matrix, and that's your matrix A in your matrix equation. Your vector is just going to be your variables in order, in this case x sub 1, x sub 2, and x sub 3. And then that final part of the augmented matrix, the augmented part, the 9 and negative 2, become the vector that ends up on the right-hand side of this equation. As we mentioned in that example, we have these equivalent ways of viewing a linear system. It can be a system of linear equations, it can be a vector equation, it can be a matrix equation, and in addition here we also saw that it can be represented by an augmented matrix. So those are all equivalent ways of representing the same idea. Here, Theorem 3 is the theorem that solidifies the fact that these representations are all representations of the same linear system. If A is an n by n matrix with columns a sub 1, a sub 2, all the way through a sub n, and if B is a vector in the m-dimensional vector space of real numbers, then the matrix equation matrix A times vector x equals vector B, that has the same solution set as the vector equation x sub 1 times vector a sub 1 plus x sub 2 times vector a sub 2, etc., plus x sub n times vector a sub n equals the vector B, which in turn has the same solution as the system of linear equations whose augmented matrix is columns a sub 1, a sub 2, all the way through a sub n, with the final column being column B. Here's a useful fact. If we have the matrix equation where we have matrix A times vector x equals vector B, that equation is only going to have a solution if and only if the vector B is a linear combination of the columns of A. If it's not a linear combination of the columns of A, you're not going to have a solution, because if you look at this in terms of the vector form of this system of equations is that the linear combination of the columns of A should give us the vector B. And so we can only have a true solution here if B is a linear combination of those columns. So it comes straight out of the vector equation for this linear system. Let's look at another example here, and here the question is, given a matrix A and a vector B, is the matrix equation matrix A times vector x equals vector B, is that a consistent equation? In other words, can there be a solution to it? For it to be a consistent system, there needs to be some type of solution. So if matrix A is 1, 4, 5, negative 3, negative 11, negative 14, and 2, 8, 10, can there be a solution to this system? So let's see what we get here. Is there a solution? Well, here's what we get. We start by considering this system as an augmented matrix, and then we go through row reduction. Now the row reduction here might look bad, but it's not that bad. What you're doing to do your row reduction here is you're doing the first row stays the same. The new second row is the old second row plus 3 times the first row. And the new third row is the old third row minus 2 times the first row. Now because 2, 8, 10 is just double 1, 4, 5, the fact that those are scalar multiples of each other indicates that at least for those 3 entries, not for the 4th entry in that row, but for those 3 entries you're going to get 0. So what happens here? Is this consistent or not? Well, the matrix equation, matrix A times vector x equals vector B, is not consistent. And the reason it's not consistent for all B is that some choices of B can make negative 2b1 plus b sub 3 not equal to 0. If you look at this entry right here, okay, if we have an entry there that is not 0, that equation now becomes an equation of the form 0 equals a non-zero number. And if 0 equals a non-zero number, well then all bets are off, because that would be complete and utter garbage, right? 0 can only be equal to 0. So if I get a number there that's not 0, we have big problems. So this is not a consistent system because there are some values for that vector b that make this nonsensical and make it inconsistent. So we cannot call this a consistent system for all b. There are some b for which it's not consistent. Let's expound on that a little bit here. This matrix equation is consistent for some b and not others. We were asking on the previous slide, is it consistent for all b? And the answer was no. But it's consistent for some b and not others. When is it consistent for a particular vector b? It's consistent for a particular vector b if the components of b satisfy the equation negative 2b sub 1 plus b sub 3 equals 0. So this system is going to be consistent for a particular plane in three-dimensional space. The plane negative 2b sub 1 plus b sub 3 equals 0. So for the points on that plane, the system is consistent, and for the points off it, it's going to be inconsistent. Furthermore, and of course you see the picture here of that plane. Now on the bottom in that blue box is the description of a situation that's not happening here. Okay? If any b in three-dimensional real vector space, if any b in three-dimensional space can be expressed as a linear combination of the columns of A, then we say that the columns of A span three-dimensional space. Now that's not happening in the previous example for the matrix A you see at the top of the screen here, because there were b that mess it up. But if any b works, then we would say that if any b can be expressed as a linear combination of the columns of A, then we would say that the columns of A span three-dimensional space. And so that's going to prompt us to a new definition of that word span. Here's our definition of span. We say that the columns of A sub 1, A sub 2, all the way through A sub p, we say they span m-dimensional space if every vector b is a linear combination of the A's. And our notation is that when we have these columns spanning, we say that the span of A sub 1 all the way through A sub p equals the space of vectors with m components. Here is a theorem that gives us some equivalent conditions. If we know one of these facts, we know all four of these facts. That's what the equivalent conditions mean. So if you have one of these four statements, you know the other three go right along with it. And here are the four statements. For each vector with m components, the matrix equation AX equals B has a solution. If that's true, then in addition, for each B, the B is a linear combination of the columns of A. In addition, the columns of A span the entire space, and the matrix A has a pivot position in every row. Now keep in mind there on that last part that when we talk about matrix A, we're talking about the regular A, not the augmented A. That's just plain A when it's before it's augmented. So if you have one of these conditions, you have all four. Let's go ahead in the next slide and take a look at the proof of this. Here's a proof of this theorem. I apologize for the small print if you're watching on a smaller space here. The font might be kind of small on this one, but here's the proof. First of all, we have these four statements, and we need to show that they are all equivalent to the same thing. But right off the bat, we know that the first three are going to be logically equivalent, because the way we defined that matrix equation, AX equals B, we know that A and B are going to be equivalent, and for C, that's just going to fall out of the way that we defined span on the previous slide. So those three are all equivalent right from the get-go. So to show that these are logically equivalent, we need to show that these statements are either all true or all false at the same time. And since A, B, and C already go together, it's just a matter of showing that when A is true, D is true, and that when A is false, D is false. And vice versa, which is actually how it's written there. Alright, so let's start at the beginning here. Suppose D is true. Okay, suppose D is true here. Now, if D is true, that's saying that you have a pivot position in every row. If we have a pivot position in every row, then let's row reduce the augmented matrix. And when we row reduce the augmented matrix, we're going to get a matrix U augmented with a final column D, and each row of U is going to have a pivot position. If all the pivot positions are in U, then there is not a pivot in D, and if there's no pivot position in D, that's a good thing, because now you know that your matrix system is going to have a solution. And so A, as it turns out, then would have to be true. Okay, conversely, suppose that D is false. If D is false, that means that if D is false, then you don't have a pivot position in every row. And if you don't have a pivot position in every row, then when we go through our row reduction, the final column there is going to be all zeros. The final row on the bottom will be all zeros. Okay, because there's no pivot position in it. And if that final row is all zeros, then what happens? Well, if D is a vector with a 1 as the last entry, then you're going to have an inconsistent system, because you're going to have a final row of the augmented matrix that's going to be 0, 0, 0, 0, 0, 0, 1, and that tells you that it's inconsistent. If this augmented row reduced matrix is inconsistent, then so will the original augmented system. And if the original augmented system is inconsistent, then A is false. So that's a quick little summary of how to show that A and D are equivalent. It goes a little bit quick, but A and D are now equivalent, and since B and C were equivalent to A, they'll also be equivalent to D. And so all four statements are equivalent. Here's another example. Suppose A is the matrix that you see here, 1, 2, 3, 4, 5, 6, and suppose that B is the vector B1, B2, B3. Is this system consistent for all B? Well, it's not going to be consistent, and here's why. Because this matrix has only 2 columns and it has 3 rows, you're going to have 2 columns and you have at most 2 pivots. But if you have only 2 pivots, you don't have a pivot for every row. And as we saw in our theorem, if you don't have a pivot for every row, it's not going to be consistent for all possible B. There might be some B for which it's consistent, but it's not going to be consistent for all B. Okay, here's another example, and you're asking the same type of question, but from another point of view of those 4 equivalent statements. Do the columns of matrix A here span 3-dimensional space? Well, again, we can reduce this to a question of pivots using row reduction. So start our row reduction process here. Subtract 2 times the first row from the second row and get a new second row that's all zeros. And at that point, once you've got all zeros, you're going to have a row without a pivot. And if you have a row without a pivot, then your system is not consistent. And if your system is not consistent, then the columns don't span don't span R3. Earlier we looked at the product of a matrix and a vector as a linear combination of the columns of the matrix. But it may also be helpful to see this done another way, and we want to do it in a way that's going to coincide with how we multiply a matrix times another matrix in Chapter 2. So you're getting a little bit of a sneak preview of Chapter 2 here, where we multiply matrices. And the way you're going to multiply matrices is to multiply the rows of the first matrix with the columns of the second matrix. Now here, with a matrix and a vector, that vector is just going to be a single column, so we don't have multiple columns, but it still works the same way, where we can do the rows of the matrix times the column that is our vector here to get this matrix multiplication. So let's take a look at how this is going to work. If we were to do the row 1, 2, negative 3 times our only column, which is 2, 1, 6, multiply in pairs the blue, green, and purple entries respectively, and then add them up. In this case, that's going to be a 2, and a negative 18, and when we add those, we get negative 14. Now do this again, except this time let's take the second row of our matrix, and again we use the only column that we have here, and again multiply the row and the column respectively, going from left to right on the row, top to bottom on the column. So multiply the blue, the green, the purple entries as you see them here, and you'll get a 2 for the blue, a 4 for the green, and a 12 for the purple, and adding those together we get an 18. And we have one more to add here, which is the third row times the column. And our corresponding entries when we do the products are going to be negative 4, 0, and 30. And adding those together will give us 26. And now we've done that matrix multiplication, where we multiply a matrix times a vector. One final theorem about multiplying vectors times a matrix A, and it's basically that it works as a linear transformation in the language of higher math here. And what we're going to see here is that if we multiply matrix A times the sum of vectors u and v, you could do each one separately and then add them together at the end. So A times the quantity vector u plus vector v is going to be A times vector u plus A times vector v. And similarly with scalar multiplication, you can factor out that scalar multiple of C. So matrix A times the vector scalar C times vector u, that matrix times vector multiplication is the same as if you do the scalar multiple C times the product of matrix A and vector u.